Hello and welcome. Imagine a world where the very building blocks of reality are not as solid as they seem, where the fundamental components of the universe are governed by rules that defy our everyday experiences. As we delve into the smallest scales of nature, we uncover a universe governed by symmetries, mirror particles, and mysterious connections that span vast distances. What you are about to hear will take you on a journey into the strange and enigmatic world of antimatter and quantum entanglement. As we look at the universe on a human scale, everything seems calm and stable. We see stars shining steadily, planets gracefully orbiting their suns, and atoms combining to form the matter that makes up our world. However, beyond this serene exterior lies a reality that is far stranger than our daily experiences suggest. Here, at the smallest scales of nature, scientists have discovered a universe governed by symmetries and mirror particles, with mysterious connections between objects separated by immense distances. One of the most intriguing discoveries of modern physics is the existence of antimatter. For every particle that makes up ordinary matter, there exists a mirror counterpart with the same mass but opposite charge and quantum properties. This antimatter annihilates with matter, converting their mass into pure energy. This fundamental interaction leads to one of the most profound puzzles in cosmology. If the universe began with equal amounts of matter and antimatter, why is it that everything we observe today consists almost entirely of ordinary matter? In parallel, physicists delving into the quantum world have uncovered phenomena that challenge our common sense. Particles that once interacted can become entangled, meaning their properties remain linked even when separated by vast distances. In this state of entanglement, measuring one particle immediately determines the state of the other, no matter how far apart they may be. The exploration of antimatter and entanglement leads scientists to question the very origins of the universe, the nature of time, and the fundamental structure of spacetime itself. These concepts unveil a cosmos that is deeply interconnected and far more mysterious than it appears. Antimatter is no longer an abstract or hypothetical idea. It is a real material composed of antiparticles that mirror the particles forming ordinary matter. For instance, an electron, which carries a negative charge, has an antiparticle counterpart known as a positron, which has the same mass but a positive charge. Protons have antiprotons, and neutrons have antineutrons. Despite their opposite charges and quantum numbers, these particles behave almost identically to their matter counterparts. They possess mass, interact with forces such as electromagnetism and gravity, and can even combine to form atoms. In laboratory experiments, scientists have successfully created atoms of antihydrogen by combining antiprotons with positrons. A crucial difference emerges when matter and antimatter come into contact. Their opposite quantum properties mean they cannot coexist, leading to their mutual annihilation. This interaction converts their entire mass into energy, illustrating the profound relationship between mass and energy that governs the physical world. Instead of leaving behind fragments of matter, these particles vanish, releasing intense bursts of radiation and energetic particles. Even the smallest amounts of antimatter can release enormous amounts of energy when annihilation occurs. Detecting antimatter, which annihilates upon contact with ordinary matter, requires meticulous experimental techniques. One common approach is to observe the radiation produced during annihilation events. When an electron meets a positron, they typically convert into two gamma-ray photons traveling in opposite directions. By detecting these photons, scientists can pinpoint where annihilation took place, a method widely used in particle physics and medical imaging. In particle detectors, antiparticles can be identified by the paths they leave while moving through magnetic fields. Charged particles curve as they traverse a magnetic field, with the direction of the curve depending on the charge sign. Since antiparticles carry opposite charges compared to ordinary particles, their paths curve in the opposite direction. This simple distinction allows scientists to differentiate between particles and antiparticles in high-energy experiments. Magnetism plays a pivotal role in studying and controlling antimatter. Many particles and antiparticles carry an electric charge, leading to strong interactions with magnetic fields. A charged particle moving through a magnetic field experiences a force that bends its path, For example, an electron curves in one direction, while a positron curves in the opposite direction due to its reverse charge. This property makes magnetic fields invaluable for detecting antimatter. In particle accelerators and detectors, scientists utilize powerful magnets to guide and analyze particle trajectories. Observing how particles curve can reveal whether they are dealing with matter or antimatter. Magnetic fields are also essential for storing antimatter. Because antimatter annihilates upon contact with ordinary matter, it cannot be placed inside regular containers. Instead, charged antiparticles are trapped using combinations of electric and magnetic fields that suspend them in empty space within a vacuum chamber. These devices prevent the particles from touching the container walls, allowing them to remain confined in the center of the trap. Using these methods, scientists have managed to create and store small amounts of antimatter, albeit for short periods. Neutral antimatter atoms, such as antihydrogen, are more challenging to control due to their lack of net electric charge. However, even in these cases, subtle magnetic effects can be harnessed to trap them using specially designed magnetic fields. Without magnetism, modern antimatter research would be virtually impossible. One of the fundamental questions that physicists have explored concerns the gravitational behavior of antimatter. Does antimatter fall downward in a gravitational field just like ordinary matter, or could it behave differently? According to modern theories of gravity, gravity acts on mass and energy rather than electric charge. This suggests that antimatter should respond to gravity in the same way as matter. For many years, this prediction remained untested because producing and trapping antimatter atoms was extremely difficult. However, recent experiments have succeeded in releasing antihydrogen atoms from magnetic traps and observing their motion in Earth's gravitational field. The results show that antimatter falls downward just like ordinary matter, indicating that gravity does not distinguish between matter and antimatter. To understand how matter and antimatter interact, consider a simple encounter between two atoms, a hydrogen atom and an anti-helium atom. A hydrogen atom consists of one proton in its nucleus with a single electron orbiting around it. An anti-helium atom is the antimatter equivalent of helium, with a nucleus containing two antiprotons and two antineutrons, while two positrons orbit the nucleus. As these atoms approach one another, several reactions occur. The hydrogen electron is attracted to one of the positrons from the anti-helium atom. When they meet, they annihilate, producing energetic gamma-ray radiation. Subsequently, the hydrogen proton may collide with one of the antiprotons in the anti-helium nucleus, resulting in a shower of energetic particles like pions, along with high-energy radiation. Even after these reactions, not all antimatter necessarily disappears. The anti-helium nucleus originally contains two antiprotons and two antineutrons. If one antiproton annihilates with a hydrogen proton, the nucleus still holds one antiproton and two antineutrons, along with a remaining positron. The remaining system resembles an antimatter version of helium-3 rather than antihydrogen. Because two antineutrons remain in the nucleus, the system is heavier than a simple antihydrogen atom. If the interaction occurs in a perfect vacuum with no surrounding matter, the remaining antimatter particles could continue to exist temporarily until they eventually encounter matter or decay through other processes. The existence of antimatter presents a profound cosmological puzzle. According to modern cosmology, the early universe following the Big Bang should have produced equal quantities of matter and antimatter. In the extremely hot environment of the early universe, particles and antiparticles were constantly created from energy and then annihilated again. If their numbers were exactly equal, all matter and antimatter would eventually have destroyed one another, leaving only radiation. Yet, the universe today clearly contains matter. Galaxies, stars, planets, and life itself are all built from ordinary particles. Physicists believe that a tiny imbalance existed in the early universe. For approximately every billion particle-antiparticle pairs created, there may have been one extra matter particle. When annihilation occurred, the pairs destroyed each other, but the small surplus of matter remained. These surviving particles eventually formed everything we observe today. Scientists continue their quest to uncover the mechanism that produced this imbalance. Certain particle interactions seem to treat matter and antimatter slightly differently, but the complete explanation remains elusive. Alongside this exploration, physicists studying the quantum world discovered another phenomenon that challenges our understanding of reality: quantum entanglement. When two particles interact under specific conditions, they can become linked in a shared quantum state. Once entangled, measuring one particle immediately determines the state of the other, regardless of the distance separating them. In quantum mechanics, entangled particles cannot be described independently. Instead, they form a single system with properties distributed across both particles. Experiments have demonstrated that entanglement can occur over distances of hundreds or even thousands of kilometers. Although these correlations appear instantaneous, they cannot be used to transmit information faster than light. Entanglement is not confined to pairs of particles. Scientists have created systems involving multiple particles sharing a single entangled state. These systems form the foundation of emerging technologies, such as quantum computing. Some physicists speculate that entanglement might play a role in the very structure of spacetime itself. In certain theoretical models, the geometry of space could arise from networks of entangled quantum states. The connection between antimatter and time emerges from the mathematics of quantum theory. When physicists studied the equations describing electrons, they discovered solutions corresponding to particles with opposite electric charge. Further analysis revealed that these solutions could be interpreted in an unexpected manner. In certain mathematical descriptions, a positron can be viewed as an electron moving backward through time. This interpretation does not imply that antimatter literally travels from the future into the past. Instead, it highlights a deep symmetry in the equations describing particle interactions. In diagrams that physicists use to visualize these interactions, an antiparticle moving forward in time can be represented mathematically as a particle moving backward through time. These symmetries suggest that the relationship between time and matter may be more intricate than our everyday experience indicates. Some interpretations of modern physics describe the universe as a four-dimensional structure in which past, present, and future coexist within spacetime. In this view, sometimes called the block universe concept, time does not flow in the conventional sense but forms part of a larger geometric structure. Although this idea does not directly solve the matter-antimatter puzzle, it implies that time itself may play a deeper role in the behavior of particles and the evolution of the universe. Understanding the relationship between time, matter, and quantum processes might eventually offer new insights into the earliest moments of cosmic history. The study of matter and antimatter reveals a universe governed by deep symmetry and delicate imbalance. Antimatter mirrors ordinary matter in almost every way, yet when the two meet, they annihilate in bursts of energy that reflect the unity of mass and energy. Magnetism enables scientists to detect, guide, and even temporarily store antimatter particles, rendering modern experiments feasible. Gravity appears to treat antimatter the same way as ordinary matter, drawing both toward massive objects. Despite these similarities, the universe today is overwhelmingly composed of matter. Somewhere in the earliest moments of cosmic history, a tiny imbalance allowed matter to survive after the great annihilation of particles and antiparticles. At the same time, quantum entanglement reveals that particles can remain connected across vast distances, hinting at deep relationships between quantum physics and the structure of spacetime. The story of antimatter and entanglement is not merely about particles. It is a narrative about the hidden architecture of reality and how the universe itself emerged from the subtle interplay of symmetry, forces, and quantum connections.